All right, today we're going to look at Giancoli 610, which we're going to deal with power. So power is how fast we do work, or the rate at which work is done. Average power is work divided by time, so it's energy that's used up during a time frame. In the SI system, we use watts to determine power. 1 watt is 1 joule per second, which is energy divided by time, so make sure we're in joules and seconds. The difference between walking and running up these stairs is power. The change in gravitational potential energy is the same. So we know we're going to start from one height and go to another. True. And that means change in energy is going to be the same. So our energy transformed is going to be equal. How fast we do it determines our power. If we run up, we do it with less time, which gives us more power. If we walk up, it takes more time, which uses less power. So power is also needed for acceleration and for moving against the force of gravity. So we can take power and we can manipulate the equation. So let's take a look at power is work divided by time. Work is force times distance over time. Distance over time is velocity. So force times average velocity gives us average power. So we can use some of that information then to find some things. And you can see from this this diagram, there's just all kinds of things we can look at when we look at a car going up a hill, and the force that's going to be required to do that. But just keep in mind, all right, that again, the same rules apply when we talk about work. Force times distance. Okay, so we will come back to this and some work with that. But here's a big equation. Average power is equal to force times average velocity. So here's an example, stair climbing power. We got a 60 kilogram jogger running up a long flight of stairs in 4 seconds. The vertical height of the stairs is 4.5 meters. So A, we want to estimate the power output in watts and horsepower, and then B, how much energy did this require? Okay, stair climbing power. So a 60 kilogram jogger runs up a long flight of stairs in 4 seconds. The height of the stairs is 4.5 meters. We want to estimate the jogger's power output in watts and in horsepower, and we'll talk about that. And then how much energy did this require? All right, so we got this going on, right? Stairs, and we're going up a height of 4.5 meters. Now, when we look at that, our initial position's here. So we're actually changing just height. So that's going to be our distance when we find our work. And then the force, right? Because all we're doing is the person is starting here with gravity and going up at the very top. We're just moving the force of gravity to get to the top. So the force of gravity is going to be mass times G, 60 times 9.8, and 60 times 9.8 gets me 588 newtons. So that's our force. So our distance and force, work, force times distance, 588 times 4.5 gives me 2646, right, joules of work. Okay, so there is our work. Now, we want to find power. Power is just work divided by time. So my work is 2646 joules over my time of 4 seconds. So 2646 divided by 4, 661.5 watts of power. Now to go from watts to, I think it's, let me look at the problem again, but I think it's at horsepower, right? Yeah. Watts to horsepower, 1 horsepower, or 1 watt, sorry, is 746 horsepower. Am I right with that? I'm sorry, I got it backwards. 1 horsepower, that's why you check your numbers, right? 1 horsepower is the same as 746 watts. So knowing that, I just got to convert my wattage to horsepower. So I say 746 watts is 1 horsepower, and 661.5 divided by 746 gives me I will go 887 horsepower. So horsepower is going to be 0.887. So we can find wattage and horsepower. as long as you remember this conversion, 1 horsepower, 746 watts. Now, how much energy did this require? Well, energy is in joules, so it required that much energy. The other way to find that energy is you could do potential energy, which is mgh, which is mg, right, times h, which would give us the same answer. So work and energy, same thing here. 14, power needs of a car. We want to calculate the power required of a 1,400 kilogram car under the following circumstances. A, it climbs up a 10-degree hill at a steady rate of 80 kilometers per hour, which is a steep hill. B, the car accelerates along a level road from 90 to 100 kilometers per hour in 6 seconds to pass another car. And we want to assume the average force, and the retarding force is just the force going backward on the car, is 70 newtons. In this case, it's probably going to be friction that we're talking about. But here's the diagram, and we will solve it now. All right, so we want to find the power required of this car, okay, to climb at a steady rate, right? So for A, we want to find the power to go at a steady rate of 80 kilometers per hour. And then B, we want to do an acceleration. Let's do part A first. So drew the quick diagram here. The force, and they call it a retarding force, that's just a slowing down force. They give you the number of 700 newtons, okay? Mass of the car is 1,400 kilograms. So what's forcing this car down is the retarding force, which is friction, air resistance, everything added all together. And then gravity's also pulling it down at this amount here, okay? So we're gonna solve for this first. mg sine of 10, mass is 1,400 times 9.8 times the sine of 10. And I get this to be 2382 newtons, okay? So now that we know this plus 700 will have to equal, right? Because our forces are balanced, right? Because we're going at a constant speed. So it's going to be force applied equals 700 plus this force, 2382, which is going to be what? 3,082 newtons is going to be the applied force to keep this thing moving at a constant speed. Now, if we want to know the power, right? Power is work divided by time. Work is force times distance divided by time, which means power also is force times change in average velocity. So we do have a force, and we do have a velocity. Our velocity is, let me find it, 80 kilometers per hour. So I want to quickly convert that to meters per second, which is 22. So now to find my power, I just take 3082 times 22, and that would be my power. So 3082 times 22 is, we're just going to give it 2 sig figs, 68,000 watts of power. I divide that by 746, and that's how much horsepower, which would be about 91 horsepower to get that done, okay? So that's part A. Now B, we're accelerating. So when we're solving for acceleration, all right, I'm going to change this to part B. When we're solving for acceleration, we got to think about our forces, right? So the sum of our forces is equal to ma. Our sum of our forces is going to be this, which is going to be the applied force, minus these two added together, right? Because this is the same, which we said was 3,082 equals the mass of our car times its acceleration. Now to find acceleration, we got to look at our speed. So it says that we go from, accelerates from a level road from 90 to 110 kilometers per hour in 6 seconds. So I'm going to break that down. Acceleration is change in velocity over change in time. Now my change in velocity, I'm going to already convert to meters per second. So we're going from 30.6 to 25. All right, so we're going from, 25 to 30.6 over the time frame of 6 seconds. So 30.6 minus 25 divided by 6 gives me an acceleration of 0.93. I substitute that in for there, and I solve for my applied force. So I take 1400 times 0.93, and then I add this over. So I add 3082. So about 4,400 newtons of force. And now we want to find the power in that, right? Let me take the force times the velocity. The velocity I would use would be the final velocity that we're getting up to, so that would be the 30.6. Sorry, power is going to be force times velocity. And I take 4384 times 30.6, and I get 134, 150 watts of power. Again, if I divide that by 746, I need 179, almost 180 horsepower to get that thing to go up.